Hello, my name is Steve Froller. I'm the owner of LCO Technologies, and I'm the manufacturer of these pumps. They're a very common format, probably the most used format of pneumatic-powered chemical injection pumps in the oil field. They've been around forever, and for good reason. It's a robust design, it is very reliable, and low cost to purchase. The problem with them is that each and every one of them is an environmental insult, including my own. There is a study done by the Persino Group, and you can make reference to it here. And what they discovered after an audit of 800 sites was that the average vent rate on a pump like this was 0.967 cubic meters per hour, or 115 tons per year of CO2e. This is the LCO Technologies Crossfire. We're going to demonstrate how we can replace 4 of these pneumatic-driven pumps with a single LCO Technologies Crossfire. And in doing so, we're going to eliminate 460 tons of CO2e from the environment, and we'll do it with using very little power. We had 3 objectives when we developed this product: efficiency, efficiency, efficiency. When we do the task of these 4 pneumatic pumps, we're going to do it with a remarkably small amount of power through exercising some pretty remarkable technology in the development of the pump, exploiting the geometry of the top works, the gearbox, and the motor, using an exotic waveform to control a variable speed drive motor. We're able to achieve quite a bit with a very small amount of power. So here we have the LCO Technologies Crossfire running with 4 half-inch fluid ends. And you can see we've got a power supply, our controller, our variable speed drive controller, and this is a true RMS multimeter that is registering the peak, the minimum, the maximum, and the average current draw. So this pump is running at 4,000 psi, 27,000 kPa, is delivering the equivalent of 150 liters a day into those sorts of conditions. And as you can see right here, the middle number is the important one. It is 2.69 amps at 24 volts, which equates to just a little over 60 watts. The next installation we're going to discuss is one of a Crossfire chemical injection pump injecting 50 liters a day into a 3,500 kPa production line, which is about 500 psi. This device right now is running at 385 milliamps, which equates to 9.25 watts at 24 volts. The number in the center is a critical number. That is the average current draw for this device. This third application is with the Crossfire chemical injection pump running at 10 liters a day, injecting into a 1,700 kPa production line, which is 250 psi. And in this case, we're running at 129 milliamps, which equates to 3 watts. So in this particular case, because we're injecting so little chemical, the pump runs intermittently. So it will run, in this particular case, for 8 seconds per minute. So the pump will choose the ideal speed to run where we're optimizing its running conditions, and then shut off for the balance of that 60-second period. So in this case, we're running for about 8 seconds, and then the pump shuts off, and after 52 seconds turns back on and delivers another batch of chemical. But every minute it's going to inject something. So the significance of the 3 watts is that for using a chemical injection pump on solar power, in environments where the temperature of the solar array can be elevated to the point where temperature compensation kicks in so hard that very, very little power actually makes it to the batteries, that small amount of power that you can get from your solar array when it's 50 degrees outside is probably more than enough to be able to run the Crossfire for the duration of the evening and probably for a few days after that. So we think that we have a solution for high temperature hostile environments that where solar is historically quite troublesome. But in this case, it's not the problem with the solar, it's the type of equipment that you're running with it. When you run the Crossfire, we think you'll be successful. Although we're running the pump intermittently in order to achieve the low volume of chemical that we are injecting in this case, whenever we start the pump, in order to eliminate inrush, we soft start the motor. This will prevent your batteries from being beat up in the field. Also, we use industry standard Textine 5100 equivalent fluid ends. As you can see, they're the same type of fluid end we're using on the pneumatic pump. The reason we do this is because we don't want to use anything that's proprietary out in the field, because this is the end that guys are going to be working on when you get these things in the field. This is the important part that is going to make the difference between having a pump that's down and failed versus one that's easily turned around. In the world of oil and gas, conventional oil and gas, more than 50% of methane venting comes from two sources: pneumatically driven chemical injection pumps and pneumatically driven instrumentation. An interesting feature about the LCO Technologies Crossfire is that by taking 4 bolts out of the bottom of the top works here, we can lift this off. You can then do maintenance on this if it's set up as a chemical injection pump. Do your maintenance in your shop instead of outside in a hostile environment. But it also allows you to convert our drive system to a solar-powered instrument air compressor. So same look and feel, same controller. Using the instrument air compressor allows you to use solar power to compress air. Now your pneumatic instrumentation is venting air instead of methane. So between the compressor and the pump, you've addressed more than 50% of all of your routine venting. Now that we've talked about the chemical injection pump and the air compressor, and we've talked a little bit about the board, we're going to cover the board in a little more detail. We have 2 controller boards. We have a basic and we have an advanced unit. The difference between them is the number of I/O and the Ethernet port on the bottom of the controller. But very straightforward. If you look at it, you'll see that there's terminals on the bottom. So we have 24 volt in, and then we have 3 phases that go out to the motor. Along the top, we have discrete ins. We have discrete ins here. We have 4 of them on the advanced. We have RS-485 communications. So this is for your Modbus communications. This is for tying into your SCADA system. This is for tying into your distributed control system. We have analog ins. So we can take multiple analog ins. So from flow transmitters, pressure transmitters, level transmitters, whatever you like. We have discrete outputs here that allow you to be able to drive things like solenoid valves. So let's say you have a 4-headed pump and you have 4 wells and 1 well goes down. Maybe you don't want to be injecting into that well that's not running. So we can stroke a solenoid valve and we can drive that chemical back to the reservoir or back to the inlet of the pump instead of wasting it flooding a well that is not running. We have an RS-232 port on the bottom where you can plug in a dongle, and now you're communicating by Bluetooth to the app on a cell phone. This RS-232 port is mirrored with the port on the top. So in applications where perhaps you'd like to have greater distance using Bluetooth, what you can do is you can run that RS-232 port to a pole top dongle, and you can you can significantly extend the range where you can sign in and use the LCO Technologies app.